Here we have to calculate the force between two straight and infinite parallel current carrying wires. Carrying currents is I1 and I2 and separated at a distance d. Let me tell you that these two wires will attract each other, as we will see shortly, and if the wires would have carried current in opposite directions, then they would have repelled each other. First, let's see why they attract each other and calculate the force. Force on, so we have to calculate force on unit length of wire. That means between these two wires there is a force. On unit length of a wire you have to find a force. Now this is this current carrying conductor is having a magnetic field near this green wire. In the vicinity of this green wire, this magnetic field B1 is having magnitude how much? Mu naught I1 by, as we have seen that formula now, due to a straight current carrying wire, mu naught I1 by 2 pi times d. You could have found it out like this also. Due to this green wire, what is the field near this, in the vicinity of this purple wire? Obviously the field will be dot and the magnitude will be mu naught I2 by 2 pi d. However, we don't need that. We need to calculate force on length 1 of this green wire. So we choose first length 1 or unit length of this wire. Make this L equal to 1. Okay, so I into L cross B, the force is in this direction. So F, force per unit length, F is force on unit length. Then we can apply the formula. What is the formula? It is IL cross B, right? So current is I2 and for length you substitute 1. It's actually ILB sin theta. So IL B1. So substitute B1 here. You get mu 0 I1 I2 by 2 pi d. You could have found out the same answer in the reverse way. That means you could have found out the force on length 1 of this purple wire. You could have got the same answer actually. I mean, you will get the same answer. Then you have to go for field B2, this dot, this field you have to find out B2. And then this current multiplied by length 1 multiplied by B2 would give you same result. Okay. Next. In this problem, this is the shell. This is a shell, and this shell carries current, right? And the direction of the current is this way. It is like an infinite wire. See, instead of the wire being of circular cross section, it is having like a half ring cross section. That means from From front it will look like this. From front view it will look like this, and the currents will be like dots. Here the dimensions are given. This is R and the current is I. Total current is I. So the shell, semicircular or the half ring carries current I as shown in figure. See, you have to find out the magnetic field at a point here, say on the axis. This is the length is infinite length. Only I have, just to show it, I have shown a cut section of it. Find magnetic field at point P. So wire is of infinite length. So this problem, you can think it like this. We have seen wires, current carrying wires. Na? This is actually collection of so many wires. See? There. You have to find the field here at point P. This is collection of so many current carrying wires of infinite length. You have to find the field at P. Now what we'll do is like this. Here choose angle theta, and here this angle will be d theta. Now this is a very small length. This is a very small length. How much is the length? The length is r d theta. And this is carrying current, very small current, di is this I, total current I, divided by, what is this total angle? Total angle pi multiplied by d theta. And due to this current carrying wire, what is the direction of the field here? See, due to a straight current carrying wire like this, you have this as a field lines like this. So due to this current carrying wire, suppose nothing else is there, you have this current carrying wire, current is a dot like this. So this is the direction of the field, dB. You will have its counterpart here, theta. Due to this wire, you have field there. So as you can see, the resultant magnetic field is in this direction. So you have to find this component. So if this is theta, then this is 90. This is 90 degrees, or this is theta. So this is actually dB cos theta. So resultant field is the integration of dB cos theta, and it is in this direction. Let us find out what is dB equal to. dB equal to mu naught di by 2 pi r. Okay, so mu naught di means I d theta divided by pi divided by 2 pi r. and multiplied by cos theta. So that is mu naught I divided by 2 pi square r. So integration of cos theta d theta. And the limit of theta is from minus pi by 2 to plus pi by 2. Here you have sin theta. Sin theta with these limits will give you 2. So mu naught I by pi square r.